Physics 1, Lab 2, Motion of a Falling Object by Root and Galwood. Today we will be going through Introduction, Real-World Experiment, Physics Concepts and Calculations, Simulation, and finally the conclusion. Starting with the introduction, we will go over a brief overview of the concepts and purpose of this lab report. The purpose of this lab is to analyze the motion of a thrown object, aka the projectile, and create a simulation that models the motion with drag and/or gravity. My group utilized a paper ball, which is the system above a table, which is the surroundings, as our tracked object. We utilized Tracker to analyze the motion, and used GlowScript to model the motion. My group's early findings in the lab were that drag force is a part of how objects move on the Earth. However, drag force is oftentimes negligible for small objects, and especially for small objects moving for a very short amount of time. Now we will be discussing the real-world experiment.
Okay, ready?
The video was then imported to the tracker, calibrated with the meter stick, and the motion was analyzed frame by frame. Then a position versus time graph was plotted via tracker. The analysis demonstrates the positions and the trajectory of the projectile as it was thrown. Next, we will be discussing the physics concepts, formulas, and processes utilized in the real-world experiment and model. Using Newton's second law, we can determine that the net force is the change in momentum over the change in time. Using this initial equation, the velocity update formula can be derived. To create our model, our group needed to find the initial velocity of the paper ball using the data from Tracker. Velocity can be calculated using the change in position and the change in time. Now let's look at the GlowScript simulation and analyze the output data. Using the provided starter code, the initial calculated conditions can be implemented. First, the mass of the paper ball was determined to be 0.0045 grams. Then the initial position used from the tracker and the initial position calculated in the model calculations are utilized. The video was then filmed for 60 frames per second, so the calculation was run at the same time step rate. Constant force of gravity in the ball can be calculated using Fgrav negative mg in the y position. After applying the initial conditions, Newton's second law is used to simulate the physics of the ball. The calculations of the ball are based on t equals 0 to t equals 1/3, so the loop is stopped when t is greater than 1/3. The drag force of each execution can be calculated with the formula Fdrag equals negative b v squared b hat, where b is the drag coefficient from the previous slide and v is the velocity of the ball. The net force can be calculated with the formula shown. Motion can be simulated without drag force if the proportionality constant b is set to 0. The animation and the graph of trajectory show a simulation of the motion of the ball without drag affecting it. The blue arrow shows the force of gravity, and the purple arrow is the velocity of the ball. Arrows are not shown to scale. Gravity and drag. Motion can be simulated with drag if the proportionality constant b is set to the value calculated in the previous slide. The animation and the graph of trajectory show a simulation of the motion of the ball with both drag and gravity affecting it. The orange arrow represents drag force, while the blue arrow represents the force of gravity. The purple arrow is the velocity of the ball. What can we conclude from this lab? Comparing the data, when the trajectory of both data sets is plotted on the same graph, it is evident that both simulations align closely with intercepts of the object, but not the path of motion. The graph supports my group's early finding that drag is negligible in this case, as the paper ball was light and not falling for long. Potential sources of error. When throwing the paper ball above the table, there was a moment where the ball was pulled down as it was thrown, giving it a downward momentum, which could have made the data less accurate. Since the camera was held during the recording, some shaking occurred, which contributed to errors in the data. Further analysis questions. Do any of your models predict terminal velocity? None of the models predict terminal velocity. The model did not run for a long enough time for terminal velocity to be present. The ball would have had to be thrown from a much higher height. An experiment could be run so that the simulation keeps running until velocity stops changing, aka F net equals 0. If the ball was thrown straight up, would it take longer to hit the table? The ball would take about 3 times as long to hit the table if it was thrown straight up as opposed to horizontally. This is evidenced by a computational model with all the velocity converted to the y velocity. Thank you for tuning in to Lab 2. Come back for Lab 3. Thank you.